Time is one of the strangest things we ever try to understand, mostly because it feels so ordinary. It is there when we wake up, when we wait for the kettle to boil, when we remember being younger, when we notice the sky darkening outside the window, and when we quietly promise ourselves that tomorrow we will definitely become the kind of person who answers emails immediately. A bold and heroic dream. Welcome to the Late Lab. It's genuinely lovely to have you here. Before we begin tonight, I'd love to know where in the world you're watching from. Are you tucked away in bed, winding down after a long day? Are you on a quiet train, watching the lights pass by the window? Are you curled up on the sofa with a blanket, a drink, and absolutely no intention of doing anything useful for the rest of the evening? Wherever you are, I hope you're comfortable, settled, and ready to let your thoughts wander gently. If you enjoy these calm little journeys through science and the stranger corners of reality, a like and subscribe really does help the Late Lab continue to grow. And if you're already subscribed, thank you. Truly, it means a lot to have you here, returning night after night as we quietly investigate the universe without raising our voices about it. Tonight, I'll do my best not to make time sound so mysterious that you end up staring at the ceiling until morning. But if that does happen, at least you'll have a better excuse than usual. You are not overthinking. You are exploring the foundations of existence, which sounds much more respectable. So let's begin. What is time, really? Why does it seem to flow from past to future? Why do clocks disagree when gravity or motion enters the story? And why does something so familiar become so strange the moment science looks at it closely? The first strange thing about time is that it rarely feels strange while we are living inside it. It feels as natural as breathing. Morning arrives, the day opens, the evening settles, and night folds itself quietly around the edges of things. We don't usually stop halfway through making tea and wonder what sort of invisible structure allows the kettle to boil after it was cold rather than before. We do not usually look at a calendar and feel shocked that Monday insists on turning into Tuesday with such confidence. Most of the time simply appears to be there, carrying everything along in the background, like a river we never chose to step into but somehow cannot step out of. And that is part of the problem. Time is so familiar that it hides in plain sight. It is the thing we use to organize almost everything else. We say when we were born, how long we slept, what hour the train leaves, how many years have passed since a childhood memory, how much longer the pasta needs before it becomes dinner rather than optimism in a pan. Time gives shape to work, rest, aging, waiting, remembering, hoping, healing, and changing. It separates breakfast from bedtime and childhood from adulthood. It lets us say that one thing happened before another, that a cause came before an effect, that a promise belongs to the future, and that a regret belongs rather inconveniently to the past. Yet the moment we try to define time clearly, it begins to slip. A simple answer might be that time is what clocks measure. That sounds sensible enough. A clock ticks, hands move, numbers change, and we agree that some amount of time has passed. But then the question quietly returns in a different coat. What is the clock actually measuring? A pendulum swings from side to side. A quartz crystal vibrates. A planet rotates. An atom changes energy states. These are physical processes repeating in regular ways. A clock does not scoop up time and pour it into little containers called seconds. It follows a change in the world and uses that change as a ruler. That does not make time imaginary. It simply means that time is not a substance we can hold, touch, or weigh. It is a physical quantity, a way of ordering events, comparing durations, and describing change. Without time, it becomes difficult to say that anything happens at all. Motion needs time, because motion means that position changes from one moment to another. Growth needs time, because a seed does not become a tree in one frozen instant. Thought needs time, because even the quietest idea has a beginning, a development, and an ending. Music needs time, because a song heard all at once would not be a song, but a very unfortunate noise. In science, time allows us to ask precise questions. How long does a falling object take to reach the ground? How quickly does light travel from the sun to Earth? How often does a heart beat? How long does a radioactive atom usually survive before decaying? How much time has passed since the early universe was hot, dense, and very different from the universe we see today? Each question depends on time as a measurable part of reality. But the familiar feeling of time is richer than measurement alone. Time is also emotional. A minute in a dentist's chair can seem to explore whole new continents of duration, while an hour with someone we love can vanish with almost suspicious efficiency. A sleepless night may feel enormous from the inside, even though the clock on the wall remains entirely unmoved by our personal objections. Boredom stretches time, fear sharpens it. Novelty makes memories dense, so that a new place may feel longer in hindsight than a month of familiar routine. The brain does not experience time like a laboratory clock. It builds the feeling of duration from attention, memory, expectation, bodily signals, and emotion. So there are already several kinds of time in view. There is clock time, measured by regular physical processes. There is biological time carried by sleep cycles, hormones, metabolism, and aging. There is psychological time, the strange inner sense that makes some moments expand and others disappear. And there is physical time, the quantity used in equations, experiments, astronomy, chemistry, and the deepest theories of the universe. The wonder is that all of these are connected, but none of them is quite the whole story. For most of human history, time was measured through cycles in nature. The sun rose and set, shadows moved. The moon changed shape in the sky. Seasons returned with a rhythm that mattered for crops, migration, shelter, and survival. The human body had its own rhythms too. Hunger, tiredness, waking, sleeping, pulse, breath. A heartbeat can serve as a rough clock, although a very emotional one. It is not ideal for precision timing, especially if the clock itself becomes nervous. Still, it shows the basic principle beautifully. Timekeeping begins by noticing something that repeats. Later, people built devices to make that repetition more reliable. Sundials used Earth's rotation and the changing direction of sunlight. Water clocks used the steady flow of liquid. Hourglasses used falling grains of sand. Mechanical clocks used gears and oscillations. Pendulum clocks, developed with great precision after the work of Christian Huygens in the 17th century, made timekeeping far more accurate. Modern atomic clocks go much further still. Since 1967, the second has been defined using a specific transition in cesium-133 atoms, involving 9,192,631,770 cycles of radiation. That is a slightly less romantic definition than a little while, but it is wonderfully useful. Atomic timekeeping reminds us that the best clocks are not magical objects. They're carefully controlled physical systems. They count regular changes in matter and energy. The more regular the process, the better the clock. And the better the clock, the more deeply we can test what time is doing. This is where the ordinary picture begins to become incomplete. In daily life, we imagine time as one universal flow. My second is your second. A clock here and a clock over there should agree, provided nobody has dropped one of them or left it near a magnet in a moment of domestic chaos. This picture works well enough for ordinary life. It is the time of appointments, birthdays, oven timers, train schedules, and messages that say, "I'm 5 minutes away," which in human language often means something much more mysterious. But physics has learned that time is not quite so simple. Time can be measured, but it is not merely a number on a clock. It can order events, but different observers may disagree about how those events are arranged in time. It can feel as if it flows, but the laws of physics do not always describe a flowing present in the way our minds expect. It can seem universal, yet motion and gravity can make clocks disagree in ways that are not mistakes. but real features of the universe. The strange truth begins here, with the gap between experience and explanation. We experience time as immediate and obvious. Science reveals it as layered and subtle. It is practical enough to tell us when to wake up, yet deep enough to challenge our ideas about reality itself. It is stitched into memory and aging, into stars and atoms, into the turning of Earth and the quiet ticking of atomic clocks. Time is not strange because it is unreal. It is strange because it is more real, more flexible, and more mysterious than it first appears. It is the familiar background of every ordinary day, and at the same time, one of the deepest questions science has ever tried to answer. Long before clocks sat on walls, glowed on phones, or quietly judged us from the corner of a laptop screen, time was read from the world itself. It was not something written in numbers. It was something felt in light, warmth, darkness, hunger, tide, weather, and shadow. Morning arrived when the eastern sky brightened. Evening came when the sun lowered and the air began to cool. A day was not yet a neat row of hours. It was a lived passage from waking to working, from heat to rest, from birdsong to firelight. This kind of time was not vague in the way we might imagine. For early human communities, noticing repeated patterns was a matter of survival. The changing height of the sun helped mark the seasons. The moon's changing shape gave a visible rhythm across the night sky. The return of cold, rain, dry heat, flowering plants, migrating animals, and fertile soil told people when to plant, when to harvest, when to travel, and when to prepare. Time was not abstract. It was food, shelter, ritual, memory, and safety. Agricultural societies depended especially on these natural cycles. A seed placed in the ground too early might fail in the frost. A harvest missed by too long might be ruined by weather or pests. So the sky became a kind of vast clock, not with hands and numbers, but with sunrise, sunsets, solstices, equinoxes, lunar phases, and the slow turning of the seasons. The universe was not yet something people measured from a distance. It was the calendar above their heads. Ancient Egypt is one of the clearest examples of this careful attention. Egyptian life was closely tied to the annual flooding of the Nile, which brought fertile silt to the land and shaped the agricultural year. Egyptian astronomers watched stars, especially the star Sirius, whose heliacal rising helped mark the approach of the Nile flood. They also divided day and night into smaller portions and used shadow clocks and water clocks to organize religious, civic, and practical life. In Mesopotamia, the Babylonians developed highly sophisticated astronomical records. They tracked the moon, planets, eclipses, and seasonal cycles with remarkable patience. Their work helped shape later traditions of calendars and mathematical astronomy. The division of the circle and the use of sexagesimal counting based on 60 left a deep mark on timekeeping. It is one reason hours and minutes are still divided in the way they are. A small echo of ancient sky watching survives every time someone says they will be there in 5 minutes, whether or not they are telling the truth. Ancient China also developed detailed calendars and astronomical observations, linking timekeeping to agriculture, imperial authority, ritual, and the prediction of celestial events. In ancient Greece, thinkers such as Aristotle considered time philosophically, connecting it to motion and change. Greek astronomers, including Hipparchus and later Claudius Ptolemy in the Roman period, helped refine models of celestial motion. Across these cultures, time was being transformed from something simply experienced into something increasingly counted, predicted, and organized. The devices people used to measure time all depended on regular physical processes. A sundial used the apparent motion of the sun across the sky, caused by Earth's rotation. As sunlight cast a shadow, the changing position of that shadow marked the passage of the day. It was elegant, simple, and rather dependent on the weather, which is always the difficulty with outsourcing your clock to the sky. Water clocks used a steady flow of liquid from one container to another. By marking levels or using controlled outflow, people could measure intervals even when the sun was not visible. Candle clocks used the regular burning of wax. Hourglasses used falling grains of sand. None of these devices captured time as a visible substance. They measured change. Water moved, wax burned, sand fell, shadow shifted. The clock was always a physical process being used as a comparison. Medieval Islamic astronomy refined timekeeping further. Scholars working in places such as Baghdad, Damascus, Cairo, and Cordoba developed astronomical tables, improved instruments, and studied the motions of the sun, moon, and planets. Accurate time mattered for calendars, navigation, and religious practice, including the timing of daily prayers and the direction of prayer. Astronomers such as Albertani and later observatory traditions, including the Moraga Observatory, contributed to a long chain of measurement and mathematical astronomy that would influence later science. Then mechanical clocks began to change the human relationship with time in a much more forceful way. In medieval Europe, mechanical clocks were used in monasteries, towns, and churches. They helped organize prayer, work, trade, and civic life. Unlike sundials, they did not depend directly on sunlight. Unlike water clocks, they could become more compact and standardized. Over time, mechanical clocks made time feel less like a natural rhythm and more like a shared structure imposed on daily life. Bells rang, work began, markets opened, meetings had a time attached to them. Humanity had discovered a way to become late in a much more precise and socially awkward manner. This mattered enormously. As clocks improved, time became portable, public, and enforceable. Railways later required standardized time because local solar time from town to town was too confusing for train schedules. Factories used clocks to organize labor. Navigation relied on accurate timekeeping, especially for determining longitude at sea. Communication across distance eventually depended on shared time standards. The more connected human societies became, the more important it was that clocks agreed with one another. The scientific importance was just as profound. Accurate clocks allowed scientists to compare motion with precision. Falling objects, swinging pendulums, planetary orbits, tides, projectiles, sound, electricity, and eventually light could all be studied more carefully because time could be measured more reliably. A major step came with Christian Huygens in the 17th century. Huygens developed the pendulum clock, using the regular oscillation of a swinging pendulum to keep time with far greater accuracy than earlier mechanical clocks. A pendulum's back and forth motion could be made remarkably steady, especially for small swings. This transformed timekeeping and helped make clocks central to physics. Regular oscillation became one of the great secrets of precision. Something repeats, and by counting the repetitions we measure duration. This shift from lived time to measured time quietly prepared the ground for modern science. Once time could be measured with increasing accuracy, it became easier to imagine it as a smooth universal background. Every event could be placed along a single line. Every motion could be compared against the same ticking standard. A stone fell for a certain duration. A planet completed an orbit in a certain period. A pendulum swung with a certain rhythm. The world seemed to unfold inside one great shared clock. And for a long time, that picture worked beautifully. The more precise the clocks became, the more tempting it was to believe that time itself must be perfectly even, perfectly universal, and perfectly independent of whatever happened inside it. Human beings had learned to trap time in clocks, but without quite realizing it, they had also built the tools that would one day reveal that time was far stranger than any clock face could show. Once humans became better at measuring time, it became easier to imagine that time itself was perfectly steady. A clock on a wall might be unreliable, a candle might burn unevenly, a sundial might become rather useless the moment clouds decide to get involved. But behind all these imperfect devices, It seemed natural to picture something deeper and cleaner. A true time, a universal time, a perfect rhythm against which everything in the universe could be measured. The clock in the room might be wrong, but time itself surely was not. This was the world in which Isaac Newton built one of the most powerful scientific pictures ever created. In Mathematical Principles of Natural Philosophy, published in 1687, Newton described time as something absolute, true, and mathematical. In his view, time flowed evenly by itself, without needing anything external to support it. It did not depend on human beings, clocks, planets, stars, or motion. Even if nothing happened, Newtonian time would still pass. Quietly, evenly, universally. The universe had a background rhythm and everything else moved within it. It is difficult to overstate how useful this idea was. If time flows the same way everywhere, then motion becomes much easier to describe. A falling apple, a fired cannonball, a swinging pendulum, and an orbiting planet can all be placed within the same framework. The same seconds apply in a garden, on a mountain, above Earth, and across the solar system. A clock in London and a clock on Jupiter might be separated by a rather inconvenient commute, but in Newton's picture they still belong to one shared time. This made the universe feel measurable in a new way. Motion was no longer just something seen and described. It became something that could be calculated. Newton's laws of motion gave scientists a way to connect force, mass, acceleration, and movement through time. An object at rest tends to remain at rest unless acted on by a force. An object in motion tends to continue moving unless something changes that motion. A stronger force produces a greater acceleration. Forces between objects come in paired interactions. These principles turned motion into a mathematical language, and time was the quiet grammar underneath it. Then Newton added universal gravitation. Every mass attracts every other mass. Earth pulls on the moon. The sun pulls on Earth. Earth pulls on the apple. The apple also pulls on Earth, although Earth handles this with slightly more dignity, because it is much larger. With gravity, Newton connected falling objects on Earth to the motion of planets in the sky. The heavens and the ground were no longer separate kingdoms governed by different rules. They were part of one system. Time made that unity possible. A planet does not simply exist in an orbit. It moves through its orbit over time. A pendulum does not simply hang. It swings with a period. A falling body does not simply change position. It accelerates as seconds pass. Newtonian physics needed a steady time coordinate, because it described how the state of a system changes from one moment to the next. Time was like the silent cosmic clock against which every event could be compared. Newton did not arrive in an empty landscape. Galileo Galilei had already helped transform the study of motion. In the late 16th and early 17th centuries, Galileo investigated falling bodies, rolling balls, inclined planes, and pendulums. His work showed the importance of measurement, experiment, and mathematical description. He helped move the question of motion away from older philosophical explanations and toward careful timing, comparison, and calculation. One of Galileo's great insights was that falling motion could be studied systematically. By using inclined planes, he slowed the motion enough to measure it more carefully. This was not just clever. It was the beginning of a new attitude. Nature could be questioned through controlled observation. Time could be used as a tool for uncovering laws. If a ball rolled down a slope, the important question was not only where it went, but how its position changed as time passed. Newton took this style of thinking and expanded it into a grand architecture. His physics explained tides, orbits, projectiles, falling bodies, and the motions of moons and planets with extraordinary success. It allowed astronomers to predict celestial motion with increasing accuracy. It gave engineers and mathematicians a reliable way to analyze forces and movement. It helped create the feeling that the universe was not a chaos of unrelated events, but a vast machine running according to precise laws. and in that machine time was absolute. This also matches ordinary intuition very well. In everyday life, we do not notice time behaving differently from place to place. A person walking down the street does not seem to age at a different rate from someone sitting on a bench. A clock upstairs does not obviously tick differently from a clock downstairs. A football, a cup of tea, a bicycle, a train, and a sleepy person trying to remember why they entered a room all appear to share the same passing seconds. For slow speeds and weak gravity, this is an excellent approximation. Newtonian time is not foolish. It is not primitive in the way people sometimes imagine older science to be. It is one of the most successful simplifications in human history. Engineers still use Newtonian mechanics to design bridges, vehicles, machines, buildings, and sports equipment. It works beautifully for ordinary speeds, ordinary distances, and ordinary gravitational fields. If you are calculating the arc of a thrown ball, you do not need to pause and worry about the deep nature of space-time. The ball will not appreciate the philosophical effort. The strength of Newton's picture is exactly why its later failure is so interesting. For centuries, universal time seemed not only useful, but almost unavoidable. It fitted the human experience of a shared present. It fitted the ticking of clocks. It fitted the movement of planets and falling bodies. It made the universe understandable without making it feel too strange. But science often becomes most interesting when a beautiful idea works almost perfectly. The cracks did not appear because Newton was careless. They appeared because measurement became more precise, and because physicists began to understand light, electricity, magnetism, and motion at very high speeds. The universe was still lawful, but the laws were quietly pointing beyond the old clockwork picture. Time still mattered, but it would no longer remain the same for everyone, everywhere, under all conditions. Newton had given the universe a perfect clock. Later, physics would discover that the clock was not as universal as it seemed. The first deep crack in universal time did not come from someone sitting in a room and deciding that time ought to be more mysterious. It came from light. For centuries, motion seemed fairly sensible. If you walk forward on a moving ship, your speed relative to the shore is your walking speed added to the ship's speed. If you throw a ball from a moving carriage, the motion of the carriage matters. Speeds combine. This feels natural because it is exactly what we see in ordinary life. Movement depends on the thing moving and on the observer watching it. There is nothing especially alarming about that. Then light began to behave as though it had read a different rule book. In the 19th century, James Clerk Maxwell brought electricity and magnetism together into one mathematical theory. Before Maxwell, electricity, magnetism, and light could seem like related but separate phenomena. Maxwell's equations showed something astonishing. Changing electric fields can create magnetic fields, and changing magnetic fields can create electric fields. Together, these linked fields can travel as waves through empty space. Light, in this picture, is an electromagnetic wave. Even more striking, Maxwell's theory predicted a definite speed for these waves. That speed matched the measured speed of light, about 300,000 kilometers per second in empty space. This was one of the great unifications in science. Light was not just brightness. It was part of electromagnetism. A candle flame, a star, a radio signal, and later the invisible waves carrying voices and images across the planet, all belong to the same broad family. But there was a problem, and it was a beautifully inconvenient one. If light is a wave, many physicists assumed it must be waving in something. Water waves travel through water. Sound waves travel through air or through another material, so it seemed reasonable to suppose that light waves travelled through a medium too. This proposed medium was called the luminiferous ether. It was imagined as an invisible substance filling space, allowing light to ripple across the universe. The ether had to be very strange. It needed to fill empty space, pass through matter, carry light waves at extraordinary speed, and somehow avoid being obvious in ordinary experiments. This is quite a demanding job description for something nobody had ever detected. Still, the idea made sense within the physics of the time. Waves needed a medium, and light appeared to be a wave, so the ether seemed like the hidden stage on which light performed. If the ether existed, Earth should be moving through it as our planet travelled around the Sun. That motion should create what physicists called an ether wind. The effect would not be a breeze one could feel on the face, which is probably just as well, as nobody wants interplanetary weather added to the forecast. It would be a subtle difference in the measured speed of light depending on whether light travelled with, against, or across Earth's motion through the ether. This was the idea Albert Michelson and Edward Morley set out to test in 1887 in Cleveland, Ohio. Their experiment used an interferometer, an instrument designed to split a beam of light into two paths at right angles, send the beams out and back again and recombine them. If one beam travelled along Earth's motion through the ether, while the other travelled across it, then the two beams should take slightly different times to return. That tiny timing difference would show up as a shift in the interference pattern, the pattern created when light waves overlap. It was an exquisitely sensitive experiment for its time. The expectation was not wild speculation. It followed from the best ideas then available about waves, motion, and the ether. If Earth was moving through an invisible light-carrying medium, careful measurement should reveal it. But the expected shift did not appear. Michelson and Morley did not detect the ether wind. No matter how the apparatus was turned, the results stubbornly refused to show the difference that classical reasoning predicted. Light seemed to travel at the same speed in the ways that mattered, even though Earth should have been moving through the ether. The universe had declined to cooperate with a very reasonable plan, which is something the universe does from time to time. It is important to be precise here. The Michelson-Morley experiment did not by itself prove Einstein's theory of relativity. Science rarely changes because of one result standing alone like a dramatic courtroom confession. Instead, the experiment became one of the major clues that the older picture was missing something. The ether was not behaving as expected. The measured speed of light was not fitting comfortably into ordinary ideas about motion. Space and time, which had seemed like a fixed background, were beginning to look suspicious. Physicists tried to save the old framework. Hendrik Lorentz and George Fitzgerald proposed that objects moving through the ether might physically contract in the direction of motion. This idea, called length contraction, could explain why the expected difference in light travel times disappeared. Lorentz developed mathematical transformations that adjusted measurements of length and time between moving observers. These ideas were not yet Einstein's full reinterpretation, but they were important steps toward it. The strange truth about time was beginning to emerge from careful measurement, not from fantasy. Light did not behave like an ordinary moving object. It did not fit neatly into the simple adding and subtracting of speeds. The failure to find the ether wind suggested that the problem was not just with light, but with the assumptions beneath motion itself. Newton's universal time had worked beautifully for falling bodies, planets, pendulums, and ordinary machines. But light was different. Electromagnetism had revealed a speed that seemed woven into the structure of nature, and once that speed was taken seriously, time could no longer remain the same simple background it had once appeared to be. Albert Einstein's great move was not to treat light as a small problem needing a clever patch. He treated it as a clue. In 1905, Einstein published his special theory of relativity, and with it, the old idea of one universal time began to change completely. The theory rested on two central principles. The first was that the laws of physics are the same for all observers moving at constant velocity. In other words, if you are gliding smoothly along in a train with no bumps, turns, or changes in speed, the basic laws of nature inside the train work the same way they do for someone standing still on the platform. The second principle was even stranger. The speed of light in a vacuum is the same for all such observers, no matter how they are moving. That sounds innocent until you think about ordinary motion. If a person throws a ball forward from a moving train, someone on the train and someone on the platform will describe the ball's speed differently. The motion of the train matters. Speeds normally add and subtract depending on the observer. But Einstein said light does not behave that way. A beam of light moving through empty space is measured at the same speed by observers moving differently. Not because their instruments are confused and not because the universe is politely hiding the answer. It is because space and time themselves adjust so that the speed of the light remains constant. This was not just a strange effect added to Newton's picture. Einstein changed the relationship between time, space, motion and observation. In Newton's universe, time was a shared background. Everyone could disagree about where something happened, depending on their viewpoint, but they would all agree about when it happened. Einstein showed that even this was not always true. The key idea is simultaneity. Two events are simultaneous if they happen at the same time. That sounds simple, because in everyday life it usually is. If two lamps flash in the same room, and we see them together, we naturally say they flashed at the same time. But when events are far apart and observers are moving differently, simultaneity becomes much less straightforward. Imagine a long train moving smoothly past a platform. A person stands exactly in the middle of the train. Another person stands exactly in the middle of the platform as the train passes. At the instant their positions line up, lightning strikes both ends of the train. To the person on the platform, the light from both strikes arrives at the same time. Since that person is halfway between the two strike points on the platform, they conclude that the lightning strikes were simultaneous. But the person on the train is moving toward the light from the front strike and away from the light from the rear strike. Because light travels at the same speed for everyone, the train observer receives the light from the front strike before the light from the rear strike. From the observer's perspective, the strikes were not simultaneous. They did not happen at the same time. This is not just a trick caused by slow vision or delayed messages. Once each observer accounts properly for the travel time of light, they still disagree about whether the distant events were simultaneous. The disagreement is built into the structure of space-time. There is no single universal present moment that all observers must share across the cosmos. The idea of now turns out to depend on motion. This is one of the strangest truths about time. The present feels immediate and obvious from inside our own experience. Yet physics does not give the universe one grand present sweeping across everything at once. A distant event that is now for one observer may belong slightly to the past or future, for another observer moving differently. For ordinary speeds, the difference is tiny beyond notice. But at speeds close to the speed of light, it becomes impossible to ignore. Special relativity also leads to time dilation. A moving clock measures less elapsed time compared with a clock that remains at rest relative to an observer. This does not mean the moving clock is broken, lazy, or making a quiet protest against responsibility. It means that time itself, as measured by physical processes, depends on motion through space-time. Experimental evidence supports this. Muons, which are unstable particles created when cosmic rays strike atoms high in Earth's atmosphere, decay very quickly when measured in the laboratory. Without relativity, many of them should vanish before reaching the ground. Yet large numbers do reach Earth's surface. From our perspective, their internal clocks run more slowly because they're moving at extremely high speeds. From the muon's own perspective, the distance through the atmosphere is shortened. Both descriptions are valid, and both belong to the same relativistic structure. The twin paradox is another famous way to feel the idea. Imagine one twin remains on Earth, while the other travels through space at very high speed and then returns. The travelling twin can come back younger than the twin who stayed behind. This is not because time travel has become a casual holiday plan, and it is not because one twin's clock malfunctioned somewhere near Alpha Centauri. The travelling twin follows a different path through space-time, and acceleration matters when they turn around and return. Different paths can contain different amounts of elapsed time. Special relativity does not say time is fake. That is the wrong lesson. Clocks still tick. Bodies still age. Particles still decay. events still happen. But time is not the same simple, universal flow Newton imagined. It is local, relational, and woven into motion. It belongs to the observer's path through space-time. The old dream of one shared cosmic now was beautiful, and for everyday life it remains useful. But light revealed something deeper. The universe does not keep time with one perfect clock placed invisibly behind everything. Each observer carries their own measure of time along their own path, and reality fits those different measures together with a precision far stranger than common sense expected. Einstein changed time by showing that it could not be separated cleanly from motion. Hermann Minkowski then gave that idea a shape. In 1908, Minkowski described a new way of understanding Einstein's special relativity. Space and time, he argued, should not be treated as two completely separate stages. They are parts of one combined structure called space-time. This was not just a convenient drawing or a poetic image. It was a mathematical way of saying that the universe does not keep space on one side and time on the other, like two neatly labelled drawers. They are woven together into a single four-dimensional framework. That phrase, four-dimensional, can sound more mysterious than it needs to. We are used to 3 dimensions of space. Something can be left or right, forward or backward, up or down. But to locate an event fully, space is not enough. If you ask where something happened, that is only part of the answer. A firework burst above a city at a certain height, over a certain street, in a certain direction. But it also happened at a particular time. Without the time, the description is incomplete. In physics, an event is something that happens at a particular place and at a particular time. A flash of light is an event. A collision between two particles is an event. A heartbeat is an event. A signal reaching a detector in a laboratory is an event. A kettle switching off after boiling water is also an event, though perhaps not one that normally gets invited into discussions of space-time. Still, it qualifies. It happens somewhere, and it happens sometime. Space-time is the structure that holds all these events together. Before relativity, it felt natural to picture space as the stage and time as the ticking clock above the stage. Objects moved around in space while time flowed steadily in the background. Minkowski's picture is different. Objects do not simply move through space while time passes separately. They trace paths through space-time. These paths are called world lines. A world line is the history of an object written into space-time. The world line of a planet curves through the solar system as the planet orbits the sun. The world line of a person begins at birth and continues through every place they go, every breath they take, every quiet evening they spend thinking about physics when they probably meant to sleep. The world line of a particle records its journey from one interaction to another. Even something that seems still, like a cup resting on a table, is not motionless in space-time. It is moving into the future along its own world line. This changes the feeling of time. Instead of imagining the universe as a sequence of separate moments, like pages being turned one after another, space-time lets physicists describe the full pattern of events and connections. Different observers may disagree about how much time passed between certain events, or how far apart those events were in space. But they agree on something deeper. That deeper quantity is called the space-time interval. The space-time interval is a combined measure of separation in space and separation in time between events. Separate measurements of distance and duration can change depending on the observer's motion. One observer may say 2 events are separated by a certain distance and a certain amount of time. Another observer, moving differently, may divide that separation into space and time differently. Yet the space-time interval remains consistent. It is the stable underlying relationship that all observers can agree on, even while their ordinary measurements differ. This is why Minkowski's view was so powerful. It showed that relativity was not simply saying everything is subjective. It was saying that some things depend on the observer, while deeper structures do not. Measured length can change. Measured times can change. Simultaneity can change. But space-time has its own geometry, and that geometry keeps the laws of physics coherent. The idea also explains why one universal present becomes so difficult to defend. Different observers slice space-time differently into what they call space now and time passing. Imagine a loaf of bread. One person cuts it straight across, another cuts it at an angle. The loaf is the same, but the slices are different. In a very loose way, observers moving differently take different slices through space-time. What counts as a set of events happening now for one observer does not have to match what counts as now for another. This does not matter much in ordinary life because our speeds are tiny compared with the speed of light. The differences are so small that human senses never notice them. Our shared now works well enough for conversation, cooking, bus timetables, and the gentle disappointment of realizing you have left your tea somewhere and it has gone cold. But across cosmic distances, or at speeds close to light, the idea of one universal now begins to break down. Space-time also gives us light cones, one of the clearest ways of understanding cause and effect in relativity. A light cone shows which events can influence which other events. From any event, light can spread outward through space as time passes. Since no physical object or information can travel faster than light in a vacuum, the future light cone contains the events that can possibly be affected by that event. The past light cone contains events that could possibly have affected it. Outside those light cones are events too far away in space and too close in time for any signal to connect them. They cannot yet influence each other, because even light would not have enough time to travel between them. This gives space-time a causal structure. It tells the universe what can be connected by cause and effect and what cannot. That is a profound shift. Time is no longer just a line along which everything marches. It is part of a geometric structure that shapes what observers measure, what events can be simultaneous, and what causes can reach what effects. Space and time are not independent containers. They are joined in the fabric of space-time, and motion determines how each observer moves through that fabric. Minkowski's famous insight was that the old separate ideas of space and time were fading into something deeper, not disappearing exactly, because we still use space and time every day, and very successfully. But beneath them lies space-time, a structure in which the ticking of a clock and the distance between places belong to the same geometry. The universe did not become less real when time became part of space-time. It became more precise. The familiar clock on the wall still measures a real process. The path of a planet still unfolds. A heartbeat still happens, quietly and locally, along one living world line. But behind all of it, time is no longer a lone universal tick. It is one part of the shape of events. Special relativity showed that motion changes the way time is measured. General relativity went further and revealed that gravity changes time too. In 1915, Albert Einstein completed his general theory of relativity. It was not just an adjustment to Newton's theory of gravity, it was a new way of understanding what gravity is. In Newton's picture, gravity was a force pulling masses toward one another through space. Earth pulled the moon. The sun pulled Earth. A dropped object fell because Earth's gravity tugged it downward. Einstein's picture was deeper and stranger. Gravity was not treated as a simple invisible force acting across a fixed stage. Instead, mass and energy shape space-time itself. Objects then move through that curved space-time along the natural paths available to them. Earth orbits the sun not because it is being yanked around in the ordinary sense, but because the sun's mass curves space-time, and Earth follows a path through that curvature. This is often described with the image of a heavy ball sitting on a stretched rubber sheet. The sheet bends, and smaller balls roll along curved paths around it. The image is useful, though not perfect, because real space-time has 3 dimensions of space and 1 dimension of time. It is not a flat sheet sitting inside another space, but as a gentle picture it helps show the central idea. Matter tells space-time how to curve, and curved space-time tells matter how to move. The astonishing part is that time is part of that curved structure. If space-time bends, then time is not immune. It does not remain an untouched background clock ticking evenly behind the scenes. In general relativity, gravity affects the rate at which time passes. A clock deeper in a gravitational field runs more slowly compared with a clock higher up. A clock closer to Earth's surface ticks very slightly more slowly than a clock farther away from Earth, such as one on a high mountain, an aircraft, or a satellite. This effect is called gravitational time dilation. It sounds at first like a problem with clocks. Perhaps gravity strains their mechanisms, or pulls on their gears, or makes them feel a little tired, which would be understandable, but that is not what is happening. Gravitational time dilation is not a mechanical fault. It affects every physical process: atomic vibrations, chemical reactions, biological processes, and the ticking of any ideal clock all follow the local rate of time in that gravitational environment. A person standing at sea level and a person standing high above Earth are not simply carrying clocks that disagree because one clock is worse. They are following slightly different paths through curved space-time. The difference is incredibly small in everyday life, but it is real. Time passes at different rates depending on gravity. One of the classic tests came from the Pound-Rebka experiment at Harvard University in 1959. Robert Pound and Glenn Rebka measured the gravitational redshift of gamma rays over a vertical height of about 22 meters in a tower. General relativity predicted that light climbing upward in Earth's gravitational field should lose energy very slightly, shifting its frequency. The experiment detected this tiny effect, supporting Einstein's prediction. It was a remarkable measurement, not because the height was enormous, but because the effect was so delicate. Modern atomic clocks make the reality of gravitational time dilation even more striking. Optical lattice clocks and ion clocks can measure time with extraordinary precision. They are so sensitive that they can detect changes in gravitational time dilation over height differences as small as centimeters. Lift one clock slightly above another, and with enough precision, the higher clock ticks just a little faster. That is a quietly astonishing fact. The floor and the table are not at exactly the same gravitational time rate. The difference is far too small for human life to notice, which is probably for the best. Nobody needs to wonder whether their head is aging faster than their feet during a quiet evening. Technically it is, by a tiny amount, but not in a way that should disturb the tea. This effect is not just a beautiful laboratory curiosity. It matters for technology we use every day. The global positioning system depends on extremely accurate timing signals from satellites orbiting Earth. Those satellites carry atomic clocks. Because the satellites are moving quickly, special relativity says their clocks should run slightly slower compared with clocks on Earth. But because the satellites are higher up, in a weaker gravitational field, general relativity says their clocks should run faster. Both effects must be included. The gravitational effect is larger than the motion effect for these satellites, so the satellite clocks run faster overall by about 38 microseconds per day relative to clocks on Earth's surface. That may sound tiny, but the global positioning system relies on light speed signals, and light travels about 300 meters in 1 microsecond. If relativity were ignored, positioning errors would grow rapidly, reaching kilometers within a day. The calm little blue dot on a navigation screen is, in its own way, an everyday monument to curved space-time. Gravity also shows its influence in much more extreme places. Near a black hole, time dilation can become enormous for a distant observer. A black hole is a region where gravity is so strong that beyond the event horizon, nothing, not even light, can escape back out to the wider universe. As an object falls toward the event horizon, a faraway observer would see its light become more redshifted and its motion appear to slow. From that distant viewpoint, the falling object seems to approach the horizon more and more slowly. But for the falling observer, their own local time feels normal. Their heartbeat continues at one beat after another. Their watch ticks in the usual local way. They do not experience their own seconds as stretched. This is one of the most important ideas in relativity. Each observer's own local clock feels ordinary. The disagreement appears when clocks in different gravitational conditions are compared. So gravity does not merely move objects, it changes the structure through which time itself is measured. A clock near a massive body and a clock far away from it do not share one perfect universal rhythm. They are both correct locally, but the universe does not force them to agree globally. This is why the old image of time as one great river becomes harder to keep. A river suggests one flow, one direction, one shared current carrying everything along equally. But real time is more subtle. Motion affects it, gravity affects it, location affects it, the shape of space-time affects it. The strange truth is not that time disappears, it is that time is woven into the physical universe so deeply that mass, motion and gravity can change how it unfolds. The second on one clock and the second on another clock may both be real, both measured carefully, and yet not match when brought back together. Time is not a single cosmic metronome. It is part of the curved architecture of reality. The strange thing about time is not only that clocks can disagree, it is that the world appears to have a direction. We do not merely experience events as scattered points in space-time, we experience them as happening in an order. Yesterday sits behind us, tomorrow waits ahead. A cup falls, hits the floor and breaks. It does not usually begin as broken pieces, leap into the air, and return neatly to the hand as a complete cup, though admittedly that would be a helpful feature in many kitchens. Coffee cools after being left on a table. Smoke spreads through a room. Ice melts in warm air. People grow older. Memories form after events happen, not before them. This one-way character of experience is called the arrow of time. The arrow of time is the direction from past to future. It is not the same as time itself, because time can be measured as duration, position in a sequence, or part of space-time geometry. The arrow of time is about direction. It is about why events seem to unfold one way and not the other. A film of a planet orbiting the sun might look physically sensible if played forward or backward, at least in a simple gravitational system. But a film of an egg smashing on the floor looks obviously wrong if played backward. The pieces gather themselves, the yolk retreats, the shell seals, and the egg jumps back to the table with impressive but deeply suspicious manners. The great scientific idea behind this everyday one-wayness is entropy. Entropy is often described as disorder, but that shortcut can be misleading. A more careful way to think about entropy is that it measures how many microscopic arrangements can produce the same large-scale state. The large-scale state is what we notice from the outside: a warm cup of tea, a room full of air, a shuffled deck of cards, a broken egg. The microscopic arrangements are the precise positions and motions of all the particles involved. There are usually vastly more ways for a system to be spread out, mixed, broken, or thermally even than there are for it to be neat, separated, unbroken, or specially arranged. Imagine a new deck of cards in perfect order. There are many ways to shuffle it into a messy-looking arrangement, but very few ways for it to remain in that special starting order. Once shuffled, the deck has not broken any deep law of physics. It has simply moved from a rare arrangement into one of the enormously many ordinary arrangements. To get back to perfect order by random shuffling is not strictly impossible, but it is so unlikely that waiting for it would require a level of patience, best described as geological, and even geology might ask to be excused. This is the heart of the second law of thermodynamics. In an isolated system, entropy tends to increase. That word tends is important. The law is statistical. It does not say every tiny microscopic motion is forced forward by a mysterious cosmic instruction. It says that when a system has many possible microscopic states, it is overwhelmingly likely to move from less probable large-scale arrangements toward more probable ones. Ludwig Boltzmann, one of the great figures of statistical mechanics, helped connect entropy with probability in microscopic states. In the 19th century, Boltzmann worked to show how the behavior of heat, gases, and thermodynamic systems could be understood from the motions of atoms and molecules. This was not a small shift. It connected the familiar world of warmth, pressure, cooling, and mixing to invisible microscopic motion. It also offered a powerful explanation for why time has a practical direction in the world we actually inhabit. Consider warm tea cooling in a room. The tea begins hotter than the surrounding air. Its molecules are moving, vibrating, and exchanging energy. Heat flows from the warmer tea into the cooler room until the temperatures become closer. The reverse process is not forbidden in the most basic microscopic sense. In principle, energy from the room's air could happen to concentrate itself back into the cup, making the tea hot again while the room cools slightly. But the number of microscopic arrangements that spread the energy out is fantastically larger than the number that gather it neatly back into the tea. So the tea cools. It does not politely reheat itself just because we forgot about it. The same idea appears in melting ice. An ice cube has water molecules held in a structured solid arrangement. In a warm room, energy flows into it, and the ordered crystal structure breaks down into liquid water. The reverse, liquid water spontaneously forming a perfect ice cube while warming the room around it, is not how ordinary experience behaves. It is not because the atoms have lost the instructions. It is because the forward process leads toward overwhelmingly more likely arrangements. Spilled milk spreads, smoke disperses, perfume drifts through air. A broken glass scatters into many pieces. These events feel irreversible, because returning to the original state would require an extraordinary coordination of microscopic motions. Every shard would need the right movement. Every molecule would need the right path. Every vibration would need to line up with absurd precision. Nature is not incapable of precision, but it does not usually organize household accidents into miracles. Here is the deeper tension. Many fundamental laws of physics work almost the same forward and backward in time. If one could reverse the positions and motions of every particle perfectly, some microscopic processes could, in principle, run backward without violating those basic equations. At that level, the laws often do not obviously announce which direction is the future, and yet the large-scale world absolutely does. This difference is one of the reasons time is so strange. The microscopic laws can be nearly time-symmetric, while the macroscopic world has a powerful arrow. The direction does not appear because every particle carries a little label saying this way to tomorrow. It appears because of probability, entropy, and the fact that the universe began in a special state from which entropy could increase. The arrow of time is also tied to memory and evidence. We remember the past because events leave physical traces. A footprint in sand records a footstep. A photograph records light that struck a sensor. A fossil records an organism preserved in rock. The cosmic microwave background records conditions from the early universe. A memory in the brain depends on changes in neural connections, chemical signals, and physical states formed after experience. The future does not leave traces in the same way. We may predict it, fear it, plan for it, or make a heroic list of tasks we will definitely complete tomorrow. But those plans are not records of future events. They are present physical states pointing toward possibilities. Evidence accumulates from what has already interacted with the world. So the arrow of time is not just an abstract idea. It is why rooms become messy more easily than they become tidy. It is why heat flows from hot to cold. It is why aging has a direction. It is why causes seem to come before effects. It is why the past is recorded and the future is anticipated. But this leaves one of the deepest questions still waiting quietly underneath everything. If entropy tends to increase, then the direction of time depends on the universe having started in a state of very low entropy. The mess grows because the beginning was unusually ordered in a very specific physical sense. To understand why time points from past to future, we eventually have to ask why the universe began in the kind of state from which an arrow of time could emerge at all. The past feels different from the future because the past has left evidence behind. That may sound obvious at first, but it is one of the most important facts about time. We do not know the past because we can reach back and touch it. We know it because traces of it remain in the present. A photograph is a present object shaped by earlier light. A footprint is a present mark shaped by an earlier step. A scar is a present change in tissue caused by an earlier wound. A memory is a present pattern in the brain shaped by an earlier experience. The past is gone in one sense, but it has not vanished without a trace. It has written itself into the world. The future is different. The future can be imagined, calculated, feared, hoped for, planned, and predicted. It can be narrowed down by evidence and physical laws, but it has not yet left records in our region of the universe. A weather forecast is not a photograph of tomorrow. A calendar entry is not evidence that the meeting has already happened, though it may be evidence that we were once optimistic enough to schedule it. The future exists for us as possibility, probability, expectation, and preparation. The past exists for us as evidence. This difference is tied closely to the arrow of time. A physical record is an arrangement in the world that carries information about an earlier event. Tree rings record seasons of growth, drought, rainfall, temperature, and environmental stress. Geological layers record sediment, volcanic eruptions, ancient seas, impacts, extinctions, and slow changes in Earth's surface. Fossils preserve traces of organisms that lived long before human memory. Written documents record decisions, laws, stories, accounts, and occasionally the eternal human struggle to write clearly. Photographs record patterns of light that once entered a camera. The cosmic microwave background records conditions from the early universe, when space was hot, dense, and filled with radiation that later stretched into microwave light as the universe expanded. All of these records exist now. They are present physical arrangements that point backward. Information theory gives us a useful way to think about this. In the 20th century, Claude Shannon helped develop a mathematical theory of information, especially in the context of communication, signals, and uncertainty. In a simple sense, information is connected to the reduction of uncertainty. A clear record tells us something that rules out other possibilities. A tree ring pattern may tell us that one year was dry. A layer of ashen rock may tell us that a volcanic eruption occurred. A photograph may tell us where someone stood, what the light was like, and whether they had been forced to smile for slightly too long. But information does not float freely outside physics. To store information, something physical must be arranged in a particular way. Ink must sit on paper. Magnetic regions must be oriented on a storage device. Neurons and synapses must change in the brain. Molecules in a fossil or mineral layer must occupy certain positions. A record requires a physical state. That means records are connected to energy, entropy, and irreversible processes. Creating a record usually involves an interaction that changes something. Light strikes a sensor. Pressure deforms sand. Heat alters material. A brain changes after an experience. These processes are not perfectly undoable in everyday life. They leave marks because the world moves along the thermodynamic arrow of time from special arrangements toward more probable ones, while making traces along the way. This is why the past feels fixed. It has become embedded in the present through records. Not perfectly, of course. Records can be incomplete, damaged, misread, or lost. A photograph can be blurred. A memory can change. A fossil can be eroded. A written account can be biased, because humans have always had a gift for being both informative and a little unreliable. But even imperfect records are still physical links to earlier events. Memory is one of the most intimate examples. We remember the past because the brain is changed by experience. When something happens, sensory systems process signals from the world. Attention selects some details more strongly than others. The hippocampus, cerebral cortex, amygdala, and other brain systems help form, organize, and strengthen memory traces. At the level of neurons and synapses, patterns of connection and activity can be altered. Eric Kandel's work on memory in sea slugs helped show how learning can involve physical and chemical changes at synapses, giving biology a concrete way to connect experience with lasting change. Memories point toward the past because they are formed after events affect the nervous system. A memory of thunder comes after sound waves reach the ears, after neural signals move through the brain, after attention and emotion help shape what is stored. We do not normally remember tomorrow's thunder because tomorrow's thunder has not yet sent sound through the air, changed the ear, altered neural circuits, or left a physical trace in the present brain. This links causality to thermodynamics in ordinary experience. Causes appear before their effects because we live inside a universe with an arrow of time. A match is struck, then a flame appears. A stone hits a window, then the glass cracks. A message is sent. Then someone receives it and wonders whether to reply now or pretend they did not see it yet. In each case, the cause produces changes that become effects, and those effects may become records. Physics can still predict future events with extraordinary precision. If the laws are known and the initial conditions are measured well enough, scientists can predict eclipses, planetary positions, radioactive probabilities, chemical reactions, spacecraft trajectories, and the behavior of many physical systems. Prediction is one of the great powers of science, but prediction is not the same as possessing a record of the future. A prediction is a present calculation based on present records and physical laws. It points forward, but it is not evidence left by an event that has already occurred. This is part of the emotional weight of time. The past can feel heavy because it has left marks. It has shaped bodies, landscapes, relationships, memories, buildings, languages, and stars. The future feels open because it has not yet settled into records around us. It has not yet written itself into tree rings, photographs, scars, fossils, or neural pathways. So the difference between past and future is not just a feeling. It is built into the way evidence works in a universe governed by entropy, information, and irreversible change. The past is known through traces. The future is approached through possibility. And every present moment is the quiet place where one becomes the other. As events happen, records form, and time leaves its fingerprints on the world. The arrow of time does not only belong to kitchens, broken cups, cooling tea, and the quiet tragedy of finding a biscuit already soft. It reaches much farther than that. If entropy explains why ordinary events move so strongly from past to future, then a deeper question appears almost immediately. Why was there room for entropy to increase in the first place? That question takes us out of the room and into cosmology. Cosmology is the scientific study of the universe as a whole. Its origin, structure, expansion, contents, and long-term evolution. It asks how galaxies formed, why space is expanding, what the early universe was like, and how the largest patterns in reality came to exist. It also gives the arrow of time a much larger setting. The direction we experience in everyday life seems to be connected not just to local messiness, but to the condition of the entire observable universe near its beginning. The Big Bang model says that the observable universe expanded from an earlier hot, dense state. This does not mean there was an explosion into empty space, as if the universe were a firework launched into a pre-existing void. It means space itself has expanded, carrying galaxies farther apart over cosmic time. When cosmologists run that expansion backward in their equations, the universe becomes hotter, denser, and more uniform. Several major lines of evidence support this picture. One is the observed recession of distant galaxies. In the 1920s, Edwin Hubble measured distances to galaxies and found that many of them appeared to be moving away from us, with more distant galaxies generally receding faster. This pattern became central to the idea of an expanding universe. Georges Lemaître, a Belgian priest and physicist, had already developed an expanding universe model from Einstein's general relativity, and he also proposed that the universe may have begun from a much denser early state. Another line of evidence comes from the abundances of light elements. The early universe was hot enough for nuclear reactions to occur, producing mostly hydrogen and helium, with smaller amounts of deuterium, helium-3 and lithium. The measured proportions of these light elements broadly match predictions from Big Bang nucleosynthesis, the theory of element formation in the first few minutes of cosmic history. Then there is the cosmic microwave background. In 1965, Arno Penzias and Robert Wilson discovered a faint microwave glow coming from every direction in the sky. This radiation is the cooled remnant of light from the early universe, released when the universe became transparent about 380,000 years after the Big Bang. Before that time, the universe was filled with a hot plasma of charged particles and radiation, and light could not travel freely for long. Once atoms formed, light could move through space, and that ancient light has been stretched by cosmic expansion into microwave radiation. The cosmic microwave background is one of the most important pieces of evidence in modern cosmology. It shows that the early universe was hot, dense, and remarkably smooth, with tiny temperature variations that later helped seed the formation of galaxies and large-scale structure. But here is the subtle part. A hot, dense early universe can sound like a high entropy state. In ordinary thermodynamics, heat spreading evenly often suggests high entropy. A gas in a box, evenly distributed and in thermal equilibrium, is usually closer to maximum entropy than a gas packed into one corner. So why do physicists say the early universe had low entropy? The answer is gravity. Gravity makes entropy much stranger than it is in a simple box of gas. Without gravity, a smooth spread of particles often represents a high entropy condition. But with gravity, smoothness can be very special. Matter that begins almost evenly distributed can later clump under its own gravitational attraction. Slightly denser regions pull in more matter. Over long periods, gas gathers into clouds, stars form, galaxies grow, and clusters of galaxies emerge. The universe becomes more structured. Under gravity, clumping can represent an increase in entropy. This feels backward at first, because clumping sounds more organized. But gravitational systems behave differently. A smooth early universe had enormous potential to form structures. As gravity amplified tiny irregularities, matter collapsed into stars, galaxies, and eventually black holes. Black holes are especially important because they are extraordinarily high entropy objects. Jacob Bekenstein and Stephen Hawking showed that black holes have entropy connected to the area of their event horizons. A universe filled with massive black holes can have vastly more entropy than a smooth early universe. So although the early universe was hot and nearly uniform, it was low entropy in a gravitational sense because matter had not yet collapsed into the high entropy structures gravity makes possible. This is why the beginning matters so deeply. Entropy has been increasing ever since because the early universe started in a very special condition. If the universe had already begun in a maximum entropy state, there would be no strong arrow of time as we know it. There would be no long story of structure forming, stars igniting, planets cooling, chemistry developing, and living beings forming memories while wondering where the evening went. Roger Penrose has emphasized this point strongly. He has argued that the early universe had an extraordinarily special low-entropy gravitational state. In his view, the smoothness of the early universe is not a trivial detail, but one of the deepest clues about the nature of time. The exact explanation for this special beginning remains debated. Cosmologists understand much about the universe's early evolution, but the ultimate reason for its low-entropy initial condition is still not settled. Cosmic inflation, is one of the major ideas connected to the early universe. Introduced by Alan Guth and developed further by Andre Linde and others, inflation proposes that the universe underwent an extremely rapid expansion during a very early fraction of a second. Inflation helps explain why the observable universe is so smooth on large scales, why it appears close to spatially flat, and how tiny quantum fluctuations could become the seeds of later cosmic structure. But inflation does not automatically solve every question about the arrow of time. In many versions, inflation itself still requires special conditions to begin. It may explain important features of the early universe, but it does not completely remove the deeper puzzle of why the universe had the kind of low entropy beginning that allowed time's arrow to unfold. So the direction of time is not just a local habit of eggs, smoke, tea, and tired people promising to tidy tomorrow. It may be rooted in the deepest history of the cosmos. Every irreversible process around us, every memory, every fossil, every star burning through its fuel, every warm object cooling into its surroundings is part of a much larger story. The universe began, as far as we can tell, in a state that allowed entropy to rise. From that special beginning came structure, change, records, stars, planets, and eventually minds capable of noticing that time only seems to move one way. The arrow of time points through every ordinary moment, but its origin may lie in the earliest conditions of everything we can observe. Time becomes stranger again when we leave planets, clocks, and galaxies behind and look down into the microscopic world. Quantum mechanics is the theory that describes matter and energy at very small scales. It is the physics of atoms, electrons, photons, atomic nuclei, molecules, and many of the processes that make chemistry, light, electronics, and modern technology possible. It is also a theory that does not describe reality in quite the same way as classical physics. In Newton's world, if you know enough about an object's position and motion, you can, at least in principle, trace a definite path. A planet follows an orbit, a ball follows an arc, a pendulum swings through a sequence of positions. Quantum systems are not usually described like that. In quantum mechanics, a microscopic system is represented by a wave function. The wave function is not a little physical wave in the everyday sense, like a ripple on water. It is a mathematical object that encodes the possible outcomes of measurements and the probabilities of those outcomes. Before measurement, an electron in an atom is not treated as a tiny planet following one neat path around a nucleus. It is described by a spread of possible properties, with certain values becoming definite only when measured. This does not mean quantum mechanics is vague or sloppy. Quite the opposite. It is one of the most precise scientific theories ever developed, but its precision is not the same as classical certainty. It gives probabilities, allowed energy levels, quantized properties, measurement outcomes, and patterns of behavior that cannot be explained by ordinary particles moving along definite paths at all times. Time has a curious role in this theory. In ordinary quantum mechanics, time usually appears as an external parameter. That means it acts like the background against which the quantum state changes. A particle may have a position that can be measured. It may have momentum. It may have energy. These can be represented as observables in the theory, but time is usually not treated as an observable in quite the same way. It sits outside the system, telling us how the wave function evolves. Erwin Schrödinger gave this idea one of its most famous forms in the 1920s. The Schrödinger equation describes how a wave function changes with time. It is precise, deterministic in its basic evolution, and central to quantum theory. If the wave function is known at one time, the equation tells us how it evolves at later times, at least before measurement enters the story. So in one sense, quantum mechanics has time built into it very clearly. The wave function evolves with time. Quantum systems change with time. Atoms absorb and emit light at particular frequencies. Unstable particles decay with measurable probabilities over time. Lasers, semiconductors, Magnetic resonance imaging, atomic clocks, and quantum experiments all depend on timing with extraordinary precision. But in another sense, time in quantum mechanics feels incomplete. It is not yet the fully dynamic, flexible time of general relativity. It is more like a clock outside the quantum system, keeping track of how the system changes. That works beautifully for many experiments, but it creates deeper questions when physicists try to combine quantum theory with gravity, where time is part of spacetime itself. The founders of quantum mechanics all had to wrestle with this new picture of reality. Werner Heisenberg developed matrix mechanics and the uncertainty principle, showing that certain pairs of properties, such as position and momentum, cannot both be known with unlimited precision. Max Born gave the wave function its probabilistic interpretation, connecting it to the likelihood of measurement outcomes. Niels Bohr became closely associated with the Copenhagen interpretation, which emphasized the role of measurement, experimental context, and the limits of applying ordinary classical pictures to quantum systems. The Copenhagen interpretation is not one single perfectly fixed doctrine, but a family of ideas associated with Bohr, Heisenberg, and others. In broad terms, it says that quantum mechanics gives us probabilities for what we may observe, and that measurement plays a special role in connecting the mathematical wave function to definite experimental outcomes. A detector clicks. A mark appears on a screen. A particle is found with a particular energy. The strange spread of quantum possibilities becomes a recorded result. Here again, time becomes subtle. The basic evolution of the wave function is largely reversible. If a quantum system is isolated and evolves according to the Schrödinger equation, the mathematics can often run forward or backward in time. It does not naturally contain the obvious one-way messiness of broken eggs, cooling tea, and remembered birthdays. At the microscopic level, many quantum laws do not strongly prefer one direction of time over the other, but measurement gives us definite records. A detector does not click unclicked. A photographic plate does not quietly remove the mark left by a particle. A laboratory notebook does not usually unwrite the result, although some handwriting makes a noble attempt. Once a measurement outcome becomes part of the macroscopic world, it is tied to thermodynamics, information, and entropy. The record is physical. It has been written into matter. This is where decoherence becomes important. Decoherence describes what happens when a quantum system becomes entangled with its surrounding environment. Heinz-Dieter Zeh and Wojciech Zurek were central figures in developing this idea. A delicate quantum superposition can remain observable only when a system is very carefully isolated. But everyday objects are constantly interacting with air molecules, light, heat, vibrations, and their surroundings. These interactions spread quantum information into the environment, making the original superposition effectively unavailable to local observers. Decoherence helps explain why the everyday world appears classical. It does not necessarily solve every philosophical question about measurement, because different interpretations of quantum mechanics still disagree about what is ultimately happening. But it explains why quantum weirdness becomes hidden at large scales. A dust grain, a cat, a cup, or a person cannot usually remain in a delicate observable superposition, because the environment is constantly taking part in the story. This connects quantum mechanics back to the arrow of time. The basic equations may be reversible, but measurement, decoherence, and thermodynamic irreversibility produce stable outcomes and records. The world we experience is not a smooth sequence of quantum possibilities visible at every scale. It is a world where interactions leave traces, where information spreads, and where records become embedded in the environment. Quantum mechanics does not prove that time is an illusion. That would be too quick, and a little too dramatic for a theory that already has enough drama to be getting on with. Clocks still work. Atomic transitions still define time with exquisite precision. Particles still change, decay, interfere, and interact. But quantum physics complicates the simple idea that reality is just a set of classical snapshots unfolding moment by moment. At the smallest scales, reality is described through probabilities, wave functions, quantist states, and measurement outcomes. Time is present, but its role depends on the framework being used. In ordinary quantum mechanics, it is usually the parameter of change. In thermodynamics, it is connected to irreversible records. In relativity, it is part of spacetime, and in the deeper search for quantum gravity, these roles do not yet fit together completely, so time is not equally straightforward in every theory. It changes character depending on the level of description. It can be the tick of an atomic clock, the parameter in a wave equation, the direction in which records accumulate, or the flexible dimension shaped by motion and gravity. The microscopic world does not remove time, but it does remind us that time is not one simple thing seen from every angle. It is a thread running through physics, and the closer we look, the more carefully that thread has to be followed. The deeper physics goes, the more time begins to behave like a question rather than a simple background. In general relativity, time is part of space-time. It can stretch, it can curve, it can run at different rates depending on gravity and motion. A clock near Earth's surface does not tick at exactly the same rate as a clock in orbit. A clock near a black hole can differ enormously from a clock far away. Time, in Einstein's theory, is not outside the universe looking in. It belongs to the physical structure of the universe itself. Quantum mechanics treats time very differently. In ordinary quantum mechanics, time usually appears as an external parameter. It is the thing used to describe how the wave function changes. The system may be quantum, uncertain, probabilistic, and delicate, but time itself often sits in the background as the steady measure of evolution. The wave function changes with time. Measurements happen at times. Probabilities are calculated for later times. But time is not usually treated as something that is itself quantum, flexible, or part of the system being described. That difference is manageable in many situations. If physicists are studying electrons in an atom, photons in an experiment, or particles in a detector, they can often use ordinary quantum mechanics extremely successfully. If gravity is weak enough, and space-time can be treated as a fixed background, the theory works with astonishing accuracy. This is why quantum mechanics can be used to explain atomic clocks, lasers, semiconductors, chemistry, and many of the technologies quietly supporting modern life. But when the question becomes the whole universe, or the inside of a black hole, or the earliest moments of cosmic history, the difference becomes much harder to ignore. Quantum gravity is the unfinished attempt to combine general relativity and quantum theory. It is one of the greatest open problems in theoretical physics. General relativity describes gravity as the geometry of space-time. Quantum theory describes matter and energy through wave functions, probabilities, fields, and quantist states. Each theory is enormously successful in its own domain, but they do not yet fit together into one complete and experimentally confirmed framework. The problem of time is one of the reasons. The conflict can be stated quite simply, even if solving it is anything but simple. In general relativity, time is dynamic. It is part of space-time, affected by mass and energy. In quantum mechanics, time is usually external. It is the parameter by which change is measured. So when physicists try to describe space-time itself quantum mechanically, they run into a strange question. If time is part of the thing being quantized, what time does the quantum system evolve with respect to? It is a little like trying to use a clock to measure the clockmaker, only to discover that the clock is also made of the thing you are trying to measure. The universe, annoyingly but impressively, refuses to stand outside itself and hold a stopwatch. A famous example of this difficulty appears in the Wheeler-DeWitt equation, associated with John Wheeler and Bryce DeWitt in the 1960s. It arose from attempts to apply quantum ideas to the entire universe. In a very broad sense, the Wheeler-DeWitt equation describes a quantum state of the universe, but in its traditional form, It does not include time in the usual way. There is no ordinary external time parameter ticking away outside the universal wave function. This has sometimes been described as a timeless equation. That can sound dramatic, as though physics has discovered that nothing ever happens and reality is secretly frozen. But that is not the careful lesson. The world plainly does not feel frozen. Stars form, particles interact, bodies age, people lose keys, find them, and then lose them again with remarkable dedication. Change is not absent from experience. The real issue is that physicists do not yet fully understand how ordinary time, the time of clocks, memories, motion, and experience, emerges from a deeper quantum description of the universe. If the most fundamental equation lacks time in the usual sense, then time may not be basic in the way we usually imagine. It may be something that appears only when the universe is described from within, through relationships between physical systems. This is where the idea of emergent time becomes important. An emergent feature is something that appears at one level of description even if it is not obvious at a deeper level. Temperature is a familiar example. A single molecule does not have a temperature in the everyday thermodynamic sense. Temperature emerges from the average motion of many particles. Pressure emerges from huge numbers of molecular collisions. The smoothness of water emerges from countless molecules behaving together, even though no single molecule is itself a puddle, which is probably for the best. Time may be similar in some approaches to quantum gravity. It may emerge from correlations between parts of the universe. One system can act as a clock for another. Change can be described relationally by comparing one physical process with another, rather than by referring to an external universal time. In this view, time is not a background container, it is a pattern of relationships. Carlo Rovelli has been one of the major physicists associated with relational ways of thinking about time, especially through loop quantum gravity. Loop quantum gravity is a research program that attempts to quantize spacetime itself. It suggests that geometry may have a discrete structure at extremely tiny scales, near the Planck scale. In this picture, space and time are not a smooth continuous stage all the way down. They may arise from more basic quantum relationships. Lee Smolin has also been an important figure in loop quantum gravity, and in broader discussions about the nature of time. Rovelli and Smolin have not always agreed on every philosophical emphasis, but both have helped shape serious scientific attempts to rethink space-time at the quantum level. Loop quantum gravity does not simply place quantum particles inside space-time. It tries to understand space-time itself as part of the quantum system. String theory approaches the problem differently. In string theory, the fundamental ingredients are not point-like particles, but tiny vibrating strings, with different vibrational patterns corresponding to different particles. String theory naturally includes gravity through a particle associated with the gravitational force, and it has inspired deep work on black holes, extra dimensions, holography, and the relationship between gravity and quantum information. Edward Witten is one of the major figures in this field, known for his work connecting string theory, mathematics, and broader ideas about fundamental physics. String theory often treats space-time in a more background-dependent way in its older forms, though later developments have explored deeper possibilities. The holographic principle in the ADS-CFT correspondence, associated with Juan Maldacena, suggests that a theory with gravity in one kind of space-time can be related to a quantum theory without gravity on a lower dimensional boundary. These ideas have led many physicists to suspect that space-time itself, including time in some form, may be connected to quantum information and entanglement. Quantum entanglement is especially interesting here. Entanglement occurs when quantum systems share a state that cannot be fully described by treating the parts separately. In some modern research, the structure of space-time appears to be deeply connected to patterns of entanglement. This does not mean space and time have been fully explained, and it certainly does not mean entanglement is a magic doorway for science fiction shortcuts. But it hints that geometry may emerge from quantum relationships rather than existing independently from the start. Thermodynamics also returns to the story. The time we experience may depend on coarse-grained descriptions where we ignore enormous amounts of microscopic detail and describe systems in terms of temperature, entropy, pressure, records, and information. The arrow of time may not be built into the deepest microscopic equations in a simple way, but it appears when systems are described statistically and when entropy increases from a special early state. So there are several possible clues. Time may be relational, it may emerge from correlations, it may be connected to entropy, it may depend on quantum entanglement, it may arise when a deeper timeless or less time-like structure is viewed from the inside by physical systems that can store records. None of these ideas is the final answer yet. That honesty matters. Some features of time are extremely well tested. Special relativity, general relativity, time dilation, gravitational redshift, atomic clocks, particle decay, and the thermodynamic arrow are not vague speculation. They are supported by experiments, observations, and technologies that work. But the deepest origin of time, especially in a complete theory of quantum gravity, remains unresolved. This does not mean science has failed. It means science has reached a boundary where two of its greatest achievements still need a deeper connection. General relativity tells us that time belongs to the shape of space-time. Quantum mechanics tells us that the microscopic world is governed by probabilities, wave functions, measurement, and quantized structure. Quantum gravity asks what time means when the geometry of the universe itself must obey quantum rules. The strange truth about time is therefore not only that it stretches, or that it flows one way, or that clocks can disagree. It is that time may not be fundamental in the simple sense we assume. It may be a feature that appears from something deeper, something involving relationships, information, gravity, and quantum structure. For now, we live with a layered understanding. Time is real in every practical sense. It is measured by clocks, felt by bodies, recorded by memory, shaped by gravity, and directed by entropy. But at the deepest level, where space-time and quantum theory meet, time becomes one of the great unfinished questions. The clock still ticks, the universe still changes, but physics is still trying to understand where the ticking ultimately comes from. Black holes are where time stops behaving like something ordinary and starts feeling like one of the universe's private jokes, told very quietly and with mathematics. They are not simply dark objects in space. They are regions where gravity has become so intense that space-time itself is shaped into a one-way structure. A black hole is a region where space-time curvature is so strong that beyond a boundary called the event horizon, future-directed paths lead inward. Once inside that boundary, moving forward in time means moving deeper toward the center. Escape is not merely difficult. It is not a matter of needing a stronger rocket, a better engine, or a more determined attitude. Beyond the event horizon, the direction that leads outward no longer lies in the possible future of anything travelling at or below the speed of light. This is why black holes are so important for understanding time. They are not just places where gravity is strong. They are places where gravity, causality, thermodynamics, quantum theory, and information all meet in a way that still challenges physics. The first exact black hole solution to Einstein's field equations came from Carl Schwarzschild in 1916, only shortly after Einstein completed general relativity. Schwarzschild found a mathematical description of space-time around a spherical mass. At the time, the full physical meaning was not obvious. Later, physicists came to understand that this solution pointed toward what we now call a black hole, a region with an event horizon, and in the simplest idealized case, a central singularity where the classical theory breaks down. The event horizon is often imagined as a surface, but that can be misleading. It is not a hard shell. If a very large black hole were approached, crossing the event horizon might not involve hitting anything solid at that exact boundary. There would be no sign saying, You're now entering the part of spacetime with extremely poor return options, although that would be helpful. The horizon is a boundary and causal structure. It marks the division between events that can still send signals to the outside universe and events that cannot. From far away, the event horizon has a strange effect on time. Imagine matter falling toward a black hole. To a distant observer, the infalling material appears to slow down as it approaches the horizon. Its light becomes stretched to longer wavelengths, a process called gravitational redshift. The signal grows dimmer and redder, fading away as the light struggles to climb out of the black hole's intense gravity. From that outside viewpoint, the falling object seems never quite to cross the horizon in a visible final moment. It slows, reddens, and disappears from view. But for the falling object itself, local time continues normally. If a person fell past the horizon of a sufficiently large black hole, ignoring for a moment the many practical objections to this plan, their own watch would tick in the ordinary way. Their heartbeat would not seem frozen to them. They would cross the horizon after a finite amount of their own proper time. Relativity allows both descriptions. The distant observer and the falling observer slice space-time differently, and extreme gravity makes the difference dramatic. This is one of the clearest examples of time being local rather than universal. There is no single master clock that says exactly what is happening everywhere from every viewpoint. Near a black hole, the disagreement between observers is not a tiny technicality. It becomes the central feature of the situation. Black holes also forced physicists to rethink which stars can support themselves against gravity. Subrahmanyan Chandrasekhar showed that white dwarf stars have a mass limit, now called the Chandrasekhar limit. Above roughly 1.4 times the mass of the Sun, electron degeneracy pressure cannot support a white dwarf against collapse. Later work on massive stars, neutron stars, and gravitational collapse helped clarify how black holes could form from the deaths of very massive stars. Roger Penrose made a major contribution by showing, through his singularity theorems, that gravitational collapse could lead naturally to singularities under broad conditions in general relativity. This helped establish black holes as serious physical consequences of Einstein's theory, not just mathematical oddities. They became part of the expected life cycle of certain massive stars, and later part of the structure of galaxies. Then Stephen Hawking and Jacob Bekenstein revealed that black holes were not completely black in the simplest thermodynamic sense. Bekenstein argued that black holes should have entropy, connected to the area of their event horizons. Hawking then showed, using quantum field theory in curved spacetime, that black holes should emit radiation. This is now called Hawking radiation. The effect is incredibly weak for large astrophysical black holes, so it is not something we expect to see glowing dramatically from ordinary black holes in the sky. But the theoretical implication is profound. Black holes have temperature. They have entropy. They connect gravity, quantum theory, and thermodynamics in one object. That is remarkable because thermodynamics is about heat, entropy, energy, and the direction of time. Quantum theory is about probabilities, fields, particles, and measurement. General relativity is about space-time and gravity. A black hole somehow brings all three into the same room and then locks the door, which is rude but scientifically productive. Hawking radiation also leads to the black hole information paradox. In quantum mechanics, information about the state of a physical system is not supposed to be fundamentally destroyed. It may become scrambled, hidden, or impossible to recover in practice, but the basic evolution of an isolated quantum system is expected to preserve information. Yet if a black hole swallows matter and eventually evaporates through Hawking radiation, it appears that information about what fell in could be lost. The outgoing radiation, in Hawking's original calculation, seemed purely thermal, carrying no detailed record of the material that formed or entered the black hole. This creates a conflict. General relativity suggests that anything crossing the event horizon cannot send information back out. Quantum theory suggests that information should not simply vanish. Thermodynamics adds entropy and radiation to the story. The result is one of the deepest puzzles in modern theoretical physics. Many ideas have been proposed to resolve it. Some involve subtle correlations in Hawking radiation. Some involve the holographic principle, where information in a volume may be encoded on a boundary. Some connect black holes to quantum entanglement and the structure of spacetime itself. But there is still no simple, settled explanation that everyone accepts in ordinary final form. Black holes remain laboratories for thought, even when they are far too distant and inconvenient to handle directly. They are not only theoretical, observations have made them part of modern astronomy. The Event Horizon Telescope collaboration produced the first image of the shadow of a supermassive black hole in the galaxy Messier 87, announced in 2019. In 2022, the collaboration released an image of Sagittarius A star, the supermassive black hole at the centre of the Milky Way. These images did not show the event horizon directly as a solid surface. They showed hot glowing material and the dark shadow created by the black hole's gravity bending light around it. That matters. Black holes are not just equations hiding in old notebooks. They shape galaxies. They form from stellar collapse. They merge and send gravitational waves through space-time, as detected by observatories such as the Laser Interferometer Gravitational Wave Observatory. They test general relativity in some of the strongest gravitational environments available to observation, and they pull the idea of time to its edge. Near a black hole, time is not the universal river of everyday intuition. It is bound to gravity and causality. It slows relative to distant observers. It points inward beyond the event horizon. It is connected to entropy through the area of the horizon. It is entangled with quantum puzzles through Hawking radiation and the information paradox. The strange truth about time becomes sharper here. Time is not merely what clocks measure in quiet rooms. It is part of the architecture that decides what can escape, what can be known, what can influence what, and whether information is truly preserved. Around black holes, time becomes a boundary, a direction, a thermodynamic clue, and a quantum mystery all at once. They are dark, but they reveal something. At the edge of a black hole, physics shows that time is tied to the deepest structure of reality, and that even our best theories still have questions waiting in the dark. After black holes and quantum gravity, it may seem almost too ordinary to return to the human body. But time is not only something measured by satellites, warped by gravity or hidden in equations. Time is also something living creatures carry inside themselves. Every organism has to deal with time. Bacteria respond to environmental cycles. Plants open and close flowers, track light, and shift their chemistry with the day. Birds migrate with the seasons. Mammals sleep, wake, feed, heal, reproduce, grow, and age through rhythms that are deeply biological. Life does not merely exist in time, it organizes itself around time. The body is full of clocks, though not clocks with hands and numbers. There are rhythms in heartbeat, breathing, hormone release, body temperature, digestion, alertness, immune activity, and sleep. There are faster rhythms in the nervous system, where neurons send electrical signals in fractions of a second. There are slower rhythms in metabolism, development, aging, and repair. A living body is not a static object being carried along by a cosmic clock. It is a system of overlapping rhythms, each one keeping time in its own way. The most familiar biological rhythm is the circadian rhythm. Circadian rhythms are roughly 24-hour cycles that help coordinate the body with the day and night cycle of Earth. In humans, the central circadian clock is located in a small region of the hypothalamus called the suprachiasmatic nucleus. It sits just above where the optic nerves cross, which is useful because light entering the eyes is one of the strongest signals for setting the body's internal time. Special cells in the retina detect light, especially blue light, and send information to the suprachiasmatic nucleus. This helps the brain judge whether it is day or night. The suprachiasmatic nucleus then helps coordinate rhythms across the body, influencing sleepiness, alertness, body temperature, digestion, and the release of hormones such as melatonin and cortisol. Melatonin tends to rise in the evening as darkness approaches, helping signal that the body should prepare for sleep. Cortisol usually rises toward morning, helping support waking and alertness. This is why light at the wrong time can disturb sleep. A bright phone screen late at night is not just a tiny glowing rectangle of questionable life choices, it is a signal to the brain. It can tell the body that the day is not quite over, even when the rest of you would very much like it to be. The molecular machinery behind circadian rhythms has been studied in great detail. Jeffrey Hall, Michael Rosbash, and Michael Young helped uncover how genes and proteins create self-regulating cycles inside cells. Their work on circadian mechanisms in fruit flies helped reveal principles that apply widely across biology, and they were awarded the Nobel Prize in Physiology or Medicine in 2017. At the cellular level, timekeeping involves feedback loops, where certain proteins build up, affect gene activity, break down, and then allow the cycle to begin again. So biological time is not just a metaphor. It is built from chemistry, genes, cells, hormones, light, and neural circuits. It is physical, measurable, and deeply connected to the environment. But there is another kind of biological time that feels even more personal, the brain's sense of duration. The brain does not appear to perceive time with a single internal stopwatch. There is no tiny clock sitting politely behind the forehead, wearing spectacles and noting that the afternoon is dragging. Instead, time perception depends on distributed systems across the brain. Attention, memory, prediction, emotion, movement, and bodily state all contribute to how long a moment feels. The basal ganglia are important for timing, movement, reward, and action selection. Dopamine signaling can influence how intervals are estimated, especially in relation to motivation, reward, and expectation. The cerebellum, often associated with coordination and fine control of movement, also contributes to precise timing over short intervals. Cortical networks help integrate sensory information, attention, planning, and memory. The hippocampus is important for memory and may help organize experiences across time. The prefrontal cortex helps with attention, decision-making, and holding information in mind. This is why psychological time is flexible. A frightening moment can feel as though it expands. The brain becomes intensely alert, attention sharpens, and later memory may contain more detail than usual. Boredom can make time feel slow because attention keeps returning to the passage of time itself. Waiting for something unpleasant can stretch minutes into small grey eternities. Meanwhile, an absorbing conversation, a good book, a game, a creative task, or a peaceful walk can make hours pass without much notice. Novelty also changes the feeling of time. When we visit a new place, the brain records many fresh details. Later, the day may feel long in memory because it contains a dense collection of new impressions. Routine can do the opposite. When days are very similar, they may pass quickly while we live them and seem strangely compressed when we look back. This is one reason childhood summers can feel enormous in memory, while adult months sometimes disappear into a blur of emails, laundry, and wondering why there are never enough clean teaspoons. Sleep deprivation changes time too. When the brain is tired, attention becomes unstable, reaction times slow, emotions become harder to regulate, and the sense of time can become distorted. A sleepless night can make the early hours feel unreal, stretched, or oddly disconnected. The body's internal clocks keep working, but the brain's ability to organize experience becomes less smooth. Emotion matters as well. Fear, grief, excitement, boredom, joy, and anxiety all shape the brain's private clock. time does not actually speed up or slow down in the physical sense because we are nervous or happy. A laboratory clock continues to tick in its own measured way. But the experience of time is produced by the brain, and the brain is part of the body. It is affected by heart rate, hormones, attention, memory formation, sensory processing, and expectation. This distinction is important. Psychological time is not the same as physical time. If a meeting feels longer than a holiday, the meeting has not literally stretched space-time in the way a black hole can. Although, to be fair, some meetings make a convincing attempt. The difference is not in the external clock. It is in how the brain constructs duration from experience. But psychological time is not meaningless just because it is subjective. It is still real as a biological process. The feeling of a long wait, a fast evening, a slow, fearful second, or a vanished afternoon comes from actual activity in the nervous system. It is produced by neurons, neurotransmitters, body signals, attention, prediction, and memory. The experience is not fake. It is simply not the same kind of time measured by an atomic clock. This gives the strange truth about time another layer. In physics, time can stretch with motion and gravity. In thermodynamics, time has a direction because entropy increases. In cosmology, the arrow of time may reach back to the early universe. In biology, time becomes rhythm, aging, sleep, hormone cycles, neural timing, and lived experience. The same universe contains relativistic time in satellites and the feeling that a dull meeting lasts longer than a holiday. Both matter. One helps navigation systems work. The other shapes what it feels like to be alive. Time is not just out there, written into space-time. It is also in here, organized by cells and interpreted by brains. Every heartbeat, every sleep cycle, every memory, every moment of waiting, and every evening that slips away faster than expected is part of the way life turns physical time into experience. Time looks different depending on what kind of thing is changing. For a human being, 100 years feels enormous. It is longer than most lives. It can hold childhood, work, love, grief, memory, illness, recovery, and the slow transformation of a face in the mirror. But to a mountain, 100 years is almost nothing. To a star, it may be less than a flicker. To some particles, it is an absurdly long stretch, so long that it might as well be forever. The universe does not keep time on one scale. It reveals time through change, and different systems change at wildly different rates. At the smallest scales, events can happen with almost unimaginable speed. Atoms can absorb and emit light when electrons move between energy states. These transitions may happen in tiny fractions of a second. Some unstable particles decay so quickly that they exist only for moments far shorter than anything the human brain can directly sense. In particle physics, lifetimes can be measured in millionths, billionths, or much smaller fractions of a second. The world beneath ordinary perception is not still. It is restless, active, and fast in ways that make a ticking clock seem rather relaxed. Then there is the world of ordinary matter around us. A flame changes from instant to instant. A wave breaks in seconds. A tree grows across years. A human body develops across decades. A stone building may weather across centuries. A mountain range can rise and erode over millions of years. Continents drift across Earth's surface at speeds of only a few centimeters per year, roughly comparable to the growth of fingernails, though continents rarely need trimming and do not complain about it. The theory of plate tectonics shows that Earth's surface is made of moving plates. Over geological time, oceans open and close, mountains form, volcanoes build islands, and continents rearrange themselves. The Atlantic Ocean is still widening. The Himalayas are still rising as the Indian plate continues to collide with the Eurasian plate. These changes are slow by human standards, but they are not small. They reshape the planet. To understand such deep time, scientists need clocks built into nature itself. Radiometric dating is one of the most important tools for reconstructing the past. It relies on radioactive decay, a process in which unstable atomic nuclei change into other nuclei at predictable rates. A half-life is the time it takes for half of a sample of a radioactive isotope to decay. Different isotopes have different half-lives, making them useful for dating different timescales. Carbon-14 dating is useful for once-living material up to tens of thousands of years old. Living organisms take in carbon while they are alive, including a small amount of radioactive carbon-14. After death, carbon exchange stops, and the carbon-14 gradually decays. By measuring how much remains, scientists can estimate when the organism died, within the useful range of the method. For much older rocks, uranium-lead dating is especially powerful. Uranium isotopes decay through chains of radioactive transformations into lead isotopes over extremely long timescales. Zircon crystals are particularly useful because they can include uranium when they form, but tend to exclude lead. If lead is found inside them later, it is often the product of radioactive decay. This allows geologists to date some of Earth's oldest rocks and minerals. Arthur Holmes was one of the great pioneers of using radioactivity to estimate geological ages. In the early 20th century, he helped establish that Earth was far older than many earlier estimates had suggested. Later, Claire Patterson used lead isotope measurements from meteorites to estimate the age of Earth at about 4.5 billion years. That number is now central to modern geology and planetary science. Earth is not merely old in a casual sense. It is ancient on a scale that human imagination has to stretch to approach. Even Earth, though, is young compared with some cosmic timescales. Stars live at very different rates depending mainly on their mass. Massive stars burn through their nuclear fuel quickly. They're bright, hot, dramatic, and short-lived, at least by stellar standards. Some may live only millions of years before ending as supernovae and leaving behind neutron stars or black holes. Smaller stars live much longer. Stars like the Sun can shine for billions of years. Red dwarf stars, which are much smaller and cooler than the Sun, burn their fuel so slowly that they may last for trillions of years, far longer than the current age of the universe. The universe itself is about 13.8 billion years old. That estimate comes from several lines of evidence, including the expansion of the universe, the cosmic microwave background, and measurements made by missions such as the Wilkinson Microwave Anisotropy Probe and the Planck Space Observatory. On that scale, human civilization is extremely recent. Written history occupies only a tiny sliver of cosmic time. A single human life is brief almost beyond comparison, and yet from the inside, it is everything. Aging gives time its most personal form. Human aging is not caused by one simple mechanism. It is a broad biological process involving accumulated molecular and cellular changes. DNA can be damaged by replication errors, radiation, chemical stress, and normal metabolism. Cells have repair systems, but they are not perfect. Proteins can become damaged or misfolded. Mitochondria, the energy-producing structures inside cells, can become less efficient. Telomeres, the protective caps at the ends of chromosomes, can shorten as many cells divide. Stem cell function can decline. Inflammation, metabolism, cellular senescence, and changes in communication between cells all contribute. This does not mean aging is just wear and tear, like a machine gradually rusting. The body is alive, active, and constantly repairing itself. Aging is the long-term result of maintenance, damage, adaptation, genetic programs, environmental exposure, and chance interacting across time. It is not one clock running down, but many biological processes slowly changing together. So time is not only the tick of a second hand, it is the decay of an isotope, the drift of a continent, the burning of a star, the formation of a fossil, the cooling of a planet, the folding of a protein, the healing of a wound, and the remembering of a childhood day that somehow feels both distant and near. different physical systems reveal time through different kind of change. Some changes are too fast to sense, some are so slow they seem frozen. A mountain appears still because our lives are short. An atom appears strange because its changes are too quick and too small for ordinary perception. A star seems eternal because it lives beyond human scales, yet it too has a beginning, a lifetime, and an end. The strange truth about time is that no single human scale is the natural one. Our clocks and calendars are useful because they match our lives. But reality stretches from subatomic flickers to cosmic ages, from a particle's brief existence to the long future of red dwarf stars. Time is not only something we count, it is the way change becomes visible across every scale of the universe. The present moment feels like the simplest part of time. The past is memory, the future is imagination. The present is here. It is this breath, this sound, this thought, this small island of experience on which we seem to stand. Whatever else time may be doing in the equations of physics, each of us appears to live inside a vivid now. And yet, the present is one of the slipperiest parts of time to understand. Part of the difficulty is that the present feels immediate from the inside. We do not experience ourselves as carefully assembling reality from delayed signals, neural processing, bodily rhythms, and predictions. We simply seem to be here, now, in the world. A voice is heard, a cup is touched, a light turns on, a thought appears. The brain presents experience as if it is happening in one smooth, unified moment. But neuroscience suggests that the conscious present is not a single mathematical instant. It is more like a short window of integration. The brain gathers information arriving from different senses, compares it, adjusts it, predicts parts of it, and binds it into a usable experience. That window may be brief, but it is not zero. The present we feel is constructed over time. Sight, sound, touch, balance, and body signals do not arrive in the brain at identical speeds. Light travels through air far faster than sound. Signals from the eyes, ears, skin, muscles, joints, and internal organs all require processing. Neural signals themselves travel at finite speeds, depending on the type of nerve fibre, whether it is myelinated and where it is travelling. Some signals move very quickly, while others are slower. The brain has to turn this staggered arrival into the feeling of one coherent moment. A simple example is watching someone clap their hands. If they are nearby, the sight of the hands meeting and the sound of the clap seem to belong together. But light reaches you almost instantly on human scales, while sound travels much more slowly through air. At greater distances, the delay becomes obvious, as with thunder following lightning. Nearer by, the brain can bind the signals together so that the event feels unified. This is not a flaw. It is a feature of perception. The brain is not trying to produce a perfect raw copy of the outside world. It is trying to produce a stable, useful model that allows the body to act. If every sensory delay were presented separately, experience would be chaotic. You would not live in a smooth present. You would live in a badly edited documentary of yourself, with the audio slightly out of sync, which is rarely anyone's preferred condition. Touch also involves timing. A tap on the foot and a tap on the shoulder do not send signals to the brain over the same distance. Signals from the foot must travel farther through the nervous system, yet the brain often produces a coordinated sense of bodily experience. It can adjust, compare, and integrate information, so the body feels like one continuous self, rather than a collection of delayed reports arriving from various departments. This makes the present deeply biological. The now we experience is not just a point in physics. It is also a construction of the nervous system. It depends on attention, memory prediction, sensory processing, and the brain's ability to organize signals into a coherent scene. The present is not fake, but it is built. Philosophers have struggled with the present for a very long time. St. Augustine famously reflected on the difficulty of explaining time, noticing that we seem to understand it until we are asked to define it. The past no longer exists in the same way. The future has not yet arrived. The present seems to be the only thing we truly have, and yet if we try to capture it as durationless instant, it vanishes into something too thin to hold. Henry Bergson later emphasized lived duration, the flowing quality of experienced time, arguing that time as we live it is not the same as time divided into abstract units. For Bergson, the inner experience of duration mattered deeply. A minute on a clock and a minute in consciousness are not always the same kind of thing, even if the clock remains annoyingly consistent. Physics complicated the present in a different way. Albert Einstein's special theory of relativity showed that simultaneity is relative. Events that are simultaneous for one observer may not be simultaneous for another observer moving differently. Hermann Minkowski then framed space and time as parts of a four-dimensional space-time structure. In that framework, different observers can slice space-time into space and time in different ways. This means physics does not support a single universal, now extending across the entire cosmos. Each observer has a local present along their own world line. You can speak meaningfully about what is happening here, for you, now. But the idea of one grand cosmic present sweeping across all galaxies, stars, planets, and observers is not part of relativity in the simple way ordinary intuition expects. That can feel unsettling because the present is so central to experience. We naturally imagine reality as a moving spotlight, illuminating one moment at a time. The past has been lit and has gone dark. The future waits in darkness ahead. The present is the bright edge where reality is happening. In philosophy of time, this broad intuition is related to presentism. Presentism is the view that only the present is real. The past no longer exists, and the future does not yet exist. It matches common experience in some ways, because we feel ourselves living only in the present. But relativity makes simple presentism difficult, because different observers may disagree about which distant events count as present. Another view is eternalism. Eternalism holds that past, present, and future events are all part of the structure of reality, often imagined through the idea of a block universe. In this view, time does not come into existence moment by moment in the same way our experience suggests. Instead, events are laid out in space-time, and the feeling of a moving now may belong to conscious beings within that structure. A third view is the growing block view. This says that the past and present are real, while the future is not yet real. Reality grows as new events become actual. This view tries to preserve the fixedness of the past and the openness of the future, while still giving the present a special role. These are philosophical interpretations, not settled experimental facts. Physics gives strong reasons to be cautious about a universal present, but philosophy asks what that means for reality, experience, and existence. The debate remains open because the equations of physics and the feeling of being alive do not answer exactly the same question. What can be said carefully is this: the feeling of now is real as an experience. It is part of how brains organize perception, action, memory, and attention. Without a working sense of the present, we could not move through the world smoothly. We could not speak, listen, catch a falling object, follow music, or notice that we have entered a room and forgotten why, a small but noble tradition of conscious life. But the idea of one cosmic now, shared by everything everywhere, is not supported by relativity. The present that feels so obvious from within a human mind does not scale up easily to the entire universe. Our local now is intimate and powerful. The universe's structure is wider, stranger, and less obedient to human intuition. So the present moment is both real and slippery. It is real because it is the living center of experience. It is slippery because, in neuroscience, It is constructed across short windows of perception, and in physics, it is not a universal slice through all of reality. The strange truth about time is perhaps most personal here. We live inside the present, but the present is not as simple as it feels. It is a local, biological, physical, and philosophical meeting point. It is where signals are gathered, memories are formed, decisions are made, and the world becomes available to us. The now is not nothing, but it is not everything either. The idea that time might be an illusion is one of those claims that sounds simple, dramatic, and slightly dangerous to think about too late at night. It is also a claim that needs careful handling. When people say time is an illusion, they can mean several very different things. They might mean that time does not exist at all. They might mean that the flow of time is not fundamental. They might mean that the present moment is not universal. They might mean that our psychological experience of time is constructed by the brain. Or they might simply mean that physics has made time much stranger than common sense expected. Those are not the same claim. The safest place to begin is with what we know time is not. Time is not an illusion in the simple sense that nothing temporal is real. Clocks measure real physical processes. Atomic clocks count regular transitions in atoms. Particles decay at measurable rates. The global positioning system requires corrections from special relativity and general relativity, because motion and gravity affect the rates of satellite clocks. Bodies age, stars burn through fuel, radioactive isotopes decay. Entropy increases in the systems around us, producing irreversible records. A photograph, a fossil, a scar, and a memory all carry traces of earlier events. So if illusion means completely fake, time does not fit. The world changes. Processes have duration. Causes leave effects. Clocks disagree in exactly the ways relativity predicts. That is not what we usually mean by something imaginary. Nobody has to believe in time as a mysterious flowing substance in order to accept that timing, duration, sequence, and change are physically meaningful. What may be misleading is the ordinary picture of time as one universal flow moving equally everywhere. In everyday life, it feels as though the whole universe shares a single present moment. The past has happened. The future has not happened yet. The present is the thin, bright edge where reality is taking place. That image is natural because it matches human experience. We live locally. We move slowly compared with light. We inhabit weak gravitational fields. Our brains organize experience into a continuous now. Under those conditions, time feels shared, smooth, and obvious. But physics does not preserve that picture exactly. Special relativity shows that simultaneity depends on motion. Two events judged to happen at the same time by one observer may not be simultaneous for another observer moving differently. General relativity shows that gravity affects the rate at which time passes. A clock nearer to a massive object can tick more slowly than a clock farther away. Thermodynamics shows that the direction from past to future is connected to entropy and the formation of records. Quantum mechanics adds further subtlety, because microscopic systems are described through wave functions, probabilities, and measurement outcomes rather than simple classical histories at every moment. So the illusion may not be time itself. The illusion may be the idea that time is simple. One interpretation often discussed in connection with relativity is the block universe. In this view, past, present, and future events are all part of a four-dimensional space-time structure. The universe is not imagined as a three-dimensional world being constantly updated by a moving present. Instead, all events are laid out in space-time. What we call the present may be more like a local perspective within that structure than a universal feature sweeping through everything. This interpretation fits naturally with Minkowski space-time, where events have positions in both space and time, and different observers slice space-time differently into space now and time passing. In a block universe picture, the past is not physically deleted, and the future is not absolutely absent. They are different regions of space-time. But it is important not to overstate this. The block universe is an interpretation of what the mathematics of relativity suggests. It is not a direct experience. We do not feel our lives as a finished four-dimensional object. We feel ourselves moving, choosing, remembering, anticipating, and changing. Physics may describe the structure in one way, while consciousness encounters that structure from within, one moment at a time. The contrast with presentism is clear. Presentism is the view that only the present is real. The past no longer exists, and the future does not yet exist. This feels deeply intuitive. It matches the way life seems from the inside. You can remember yesterday, but you cannot visit it. You can imagine tomorrow, but you cannot hold its evidence in your hand. Only now seems fully alive. Relativity makes simple presentism difficult because it removes the idea of one universal present shared across all reality. If observers moving differently disagree about which distant events are happening now, then it becomes hard to say that only the present is real, unless we can say whose present counts. Still, presentism has not simply vanished from philosophy. Some philosophers try to defend modified versions of it, or argue that relativity does not settle every metaphysical question. The debate is not just about equations, it is also about what we mean by real. There are also more radical scientific and philosophical approaches. Carlo Rovelli has argued for a relational view of time, where time is not an absolute background but arises from relationships between physical systems. In this picture, what matters is not one grand cosmic clock, but the way systems change relative to one another. Time is tied to interaction, comparison, thermodynamics, and perspective. Julian Barber has proposed an even more radical view, suggesting that time may not exist at a fundamental level at all. In his ideas, reality can be thought of as a collection of configurations, with the appearance of time emerging from relationships between them. Some configurations contain records that give the impression of a past. This is a striking and controversial view, and it should not be presented as settled fact. But it shows how seriously some thinkers have taken the possibility that the ordinary flow of time may not be fundamental. These ideas are thought-provoking because they challenge the deepest habits of human intuition. But they are not permission to say, casually, that time is fake and then ignore the alarm clock. The alarm clock remains undefeated in practical philosophy. Science often replaces simple experience with deeper description. Earth feels still beneath us, yet it rotates once each day and orbits the sun once each year. Solid matter feels continuous and firm, yet it is made of atoms structured by electromagnetic forces and quantum fields, with most of its apparent solidity coming from interactions rather than tiny hard pieces packed edge to edge. The sky looks like a dome, but Earth is a planet in space. Common sense is not useless, but it is local. It evolved for human life, not for black holes, cosmic horizons, quantum measurement, or relativistic simultaneity. Time may be similar. Our experience of flowing time is real as experience. It helps us act, remember, plan, speak, listen, and make sense of the world. But the deeper physical description does not need to match the feeling exactly. The universe is under no obligation to arrange its foundations in the shape most convenient for human intuition, which is inconsiderate, but by now not surprising. The balanced answer is that time is real enough to structure physics, technology, memory, aging, and causality. It is real enough for clocks to measure, for satellites to correct, for particles to decay, for bodies to grow older, for stars to evolve, and for records to accumulate. But it is not simple enough to be one universal river flowing equally everywhere. So, could time be an illusion? Not in the crude sense. But the flow of time, the universal now, and the idea of one cosmic clock may be more like useful appearances than fundamental truths. Time is not nothing. It is also not what it first seems. It may be local, relational, thermodynamic, geometric, biological, and perhaps emergent at the deepest level. The strange truth is that time survives the question, but it does not survive unchanged. It remains real, powerful and measurable, while becoming less like a background stream and more like a layered feature of reality. The illusion is not that time matters. The illusion is that we ever understood it just because we learned how to read a clock. The strange truth about time is not that it is unreal. That is too simple, and perhaps a little too eager to sound mysterious. Time is not something we can dismiss as a dream, a trick, or a decorative illusion placed over the universe for dramatic effect. Clocks measure real physical processes. Particles decay, stars age, bodies change, light travels, memories form. The world does not sit motionless behind the appearance of time. Things happen, and their happening has order, duration, consequence, and trace. But time is not the simple thing it first appears to be either. The deeper truth is that time is layered. It is measured by clocks, but not created by them. It is shaped by motion, as special relativity shows, and shaped by gravity, as general relativity reveals. It is directed by entropy, because the past and future are not symmetrical in the world we actually experience. It is felt by brains through attention, memory, emotion, prediction, sleep, and biological rhythm. And at the deepest edge of physics, where quantum theory and gravity are still waiting to be fully joined, time remains one of the great unfinished questions. We began with the most ordinary version of time, the time of daily life. Morning, evening, waiting, aging, remembering, planning, and quietly wondering how 3 hours disappeared while doing something that was supposed to take 10 minutes. From there, time became something humans learned to measure. Sunrise, sunset, shadows, seasons, lunar phases, water clocks, sundials, pendulums, and atomic clocks all showed the same basic idea. A clock is not a box full of time. It is a physical process regular enough to compare other changes against. Then came Newton's great universal clock. In Isaac, Newton's classical picture, time flowed evenly everywhere, independent of the things happening inside it. It was a perfect background against which falling apples, swinging pendulums, fired cannonballs, and orbiting planets could all be measured. And for everyday speeds and ordinary gravity, this picture still works beautifully. It remains one of the most useful approximations in science. But light disturbed the simplicity. James Clerk Maxwell showed that light is an electromagnetic wave moving at a fixed speed in empty space. The Michelson-Morley experiment failed to detect the expected ether wind. Hendrik Lorentz and George Fitzgerald tried to explain the result with length contraction. Then Albert Einstein changed the foundations. Special relativity showed that the laws of physics are the same for observers moving at constant velocity, and that the speed of light in a vacuum is the same for all of them. From that came the end of one shared now. Events that are simultaneous for one observer may not be simultaneous for another. Moving clocks can measure less elapsed time. The travelling twin in the twin paradox can return younger than the twin who stayed behind. These are not clock errors. They are features of space-time. Hermann Minkowski then gave this idea its geometric form. Space and time became space-time, a four-dimensional structure of events, world lines, intervals, and light cones. Time was no longer a single ticking line behind the universe. It was part of the shape of reality. General relativity deepened the strangeness. Gravity was not simply a force pulling objects through space, but the curvature of space-time caused by mass and energy. Clocks deeper in a gravitational field run more slowly than clocks higher up. The global positioning system works because engineers account for the effects of both motion and gravity on satellite clocks. Near black holes, time becomes even more dramatic, stretched by intense gravity and tied to horizons, entropy, radiation and information. Then entropy gave time its direction. Eggs break, coffee cools, smoke spreads, records form. The second law of thermodynamics explains why isolated systems tend to move from less likely arrangements toward more likely ones. Ludwig Boltzmann helped connect this to probability in microscopic states. The arrow of time is not merely a feeling. It is written into the irreversible processes that make memory, evidence, and history possible. Cosmology widened the question. The Big Bang model shows that the observable universe expanded from an earlier hot, dense state. The cosmic microwave background, galaxy redshifts, and light element abundances all support that broad picture. But the early universe also seems to have been in a very special low-entropy gravitational state. Roger Penrose has emphasized how deep this puzzle is. The arrow of time may reach back to the earliest conditions of the cosmos. Quantum mechanics made time stranger again. In ordinary quantum theory, time usually appears as an external parameter, while wave functions, probabilities, and measurement outcomes describe the microscopic world. Decoherence, through the work of H. Dieter Zee and Wojciech Zurek, helps explain why fragile quantum possibilities become unavailable at everyday scales. But when quantum theory meets gravity, the role of time becomes deeply uncertain. The Wheeler-DeWitt equation, loop quantum gravity, string theory, and ideas of emergent time all point toward a frontier that is not yet settled. And then there is the time we feel. Biological time lives in circadian rhythms, aging, hormones, neural timing, metabolism, and sleep. The brain's private clock is not a single stopwatch, but a web of attention, memory, dopamine signaling, prediction, emotion, the basal ganglia, the cerebellum, and cortical networks. The present moment feels immediate, yet neuroscience suggests it is constructed over short windows of perception. Relativity then reminds us that this vivid local now is not one cosmic present shared across everything. So the strange truth about time is balanced. Time is physically real. Processes happen, clocks tick, particles decay, stars burn and die, bodies age, records accumulate, technology depends on precise timing. The universe would not make sense without sequence, duration, causality, and change. But time is not the simple flowing substance of ordinary intuition. There is no single universal cosmic clock ticking identically for everything everywhere. There is no obvious universal now sweeping across the entire cosmos. The past and future are not symmetrical in practice, because entropy gives the world direction. And the deepest origin of time, especially in quantum gravity, consciousness, and the earliest universe, remains unresolved. That is what makes time so quietly extraordinary. It is the thing we live inside every second, the thing we measure constantly, the thing we feel more intimately than almost anything else, and yet the thing we still do not fully possess. Time is familiar enough to set an alarm by, and strange enough to lead us to the edge of physics. The strange truth about time is that it is deeply real, and yet deeply unlike the simple flow we imagine in everyday life. It is real because the universe changes. Clocks measure physical processes. Atoms shift between energy states. Particles decay. Stars age. Bodies grow, heal, weaken, and remember. The world leaves records behind, and those records give the past its weight. Time is not merely a human invention placed over reality like a label on a jar. It is woven into motion, change, evidence, aging, and the practical working of science. But it is not one single river flowing identically everywhere. Human beings first learned time from the sky, from sunrise and sunset, shadows and seasons, ancient clocks and careful calendars. Newton gave time a perfect universal rhythm, a background against which apples, planets, pendulums, and projectiles could all move. Then Maxwell's light, Michelson and Morley's experiment, Einstein's relativity, and Minkowski's spacetime revealed something stranger. time could not be separated so cleanly from space, motion, gravity, or observation. General relativity showed that gravity changes the rate of clocks. Entropy gave time a direction. The early universe raised the question of why that direction exists at all. Quantum mechanics made time more subtle at microscopic scales, while quantum gravity left its deepest origin unresolved. Black holes tied time to horizons, information, heat, and mystery. Biology brought time back into the body through circadian rhythms, aging, memory, attention, and the vivid feeling of now. So time is not an illusion in the simple sense. Relativity, time dilation, entropy, and clock physics are strongly supported. Our technologies depend on them. Our bodies live through them. And yet the final nature of time, especially in quantum gravity and consciousness, remains unfinished. Every quiet second carries more than it seems. The turning of Earth, the aging of stars, the rhythm of cells, the memory of the past, and the still open question of what time really is.